So last time we met, page up, right? We talked about electromagnetic spectrum, what made up light. What made up light again, Melissa? What does light consist of? All light? What does it consist of?
Energy.
Yeah, but what two fields?
Oh, magnetic and electric.
Magnetic and electric fields, yeah. And talked about, since we're going to do spectroscopy, the interaction between light and matter, we had to get light into just certain frequencies, not have them all blast our sample, right? And so then we have things like dispersing elements. And if we don't want to use a dispersing element, we could monitor all wavelengths at the same time, all intensities, see how they're all these different intensities are changing at different frequencies, monitor them all at the same time. You can do Fourier transform. But you have to have a little mechanical thing in there to make that transition, to do that kind of thing. And then we jumped into spectral lines. Now they're talking about gases. That's the only thing that can generate lines, spectral lines. And they kind of look like what we have drawn there. And they introduced the, like the incident intensity, right? Incident intensity and transmitted intensity, and then you could measure things like transmittance or absorbance, right? So there's expressions to that to actually measure the attenuation of light, right? Okay, so we'll pretty much wrap up this first day, so there'll be homework due over the weekend. But now they're jumping into stimulated absorption. And all they're doing is absorption, whether it's stimulated or not. So it's the exact same absorption we were talking about before. But this is for just one molecule. This is just for one molecule. So they're saying little omega is the transition rate. So the rate of a molecule going from what state to what state, probably, if we're talking about absorption. Going from, how do we label these? Yeah, we kind of label them as E0 to E1. And what did you say, Melissa? From what state to what state? Ground state to an excited state. Exactly. So that's our absorption idea. So we're just talking about one molecule is all. So that's stimulated absorption rate, the rate at which a molecule will go to its excited state from the ground state, right? That's equal to B, this Einstein coefficient of stimulated absorption, times rho, which is the energy density at the transition frequency. So, right, this difference in energy, say that's delta E. But in terms of a photon, Gloriana, how'd they write that? That's energy separation E1 minus E0 is really just, how do we write the energy of a photon? H, anybody help her? H nu, right? So that's what they're talking about. So you shine light that's at that frequency, right? And it'll absorb. But energy density, I don't think we've ever used the words, oh, the energy density is so bright. We don't use the word energy density. We use the word intensity. Right? Oh, it's so intense. But whatever, right? So they're just saying that, does that make sense then? That the more intense, the higher the energy density at that frequency, yeah, your transition rate should go even more likely and faster. You should have more of them per unit time. It kind of makes sense, right? If you have very dim light versus very intense light, that's going to really affect your transition rate, the rate of one molecule going from ground state to excited state. So, and then, okay, you have well, hardly ever have one molecule. You have a bunch of them. So N would be if you want the total rate of absorption, that's big W now. You multiply N times the transition rate of a single molecule. So N must be the number of molecules, all of them, right? Because now they're talking about a whole bunch of molecules. So the total rate of absorption, all the molecules, and again, we're talking about gases, and So the total rate of absorption is just the number of molecules times that single, the transition rate of an individual molecule. And this figure 1611, they're trying to say the two ways, or the two modes of emission. Okay. One of them is, let's just talk about the complicated one first since it's right here. Stimulated emission. Stimulated emission. So if a molecule is going to emit light, first off, it has to be in what state? Excited state. So now we're talking about absorption anymore. Absorption must have already happened. So it absorbed, and now it's in its excited state. Okay, now to get back to the ground state, it's going to emit light. It doesn't have to. We're just talking about emission. So not all molecules are going to be emitters, but okay. So we're going to reach the ground state through emitting light. And there's two ways to emit light. The first one is stimulated emission. And I like this diagram. Okay, I like what they're showing here. Right? I'm kind of picturing, right, the molecule being here. It's in its excited state, right, because that's energy. And they kind of left off all this stuff, right? But the molecule's right there. And so that means, and what did this squiggly line mean again, Kevin? What did this squiggly line mean again? What did it mean again? They're using it to represent what?
The wave.
Yeah, a wave.
And then light.
Light. And what part of the light?
The particle.
What part of the light? Lois?
The electric.
The electric field, exactly, right? So they're not trying to make this, draw this three-dimensional nice picture of light and drawing all its components and how it's a transverse wave and all this stuff. No, they're just showing the electric field of light. Okay, so that's the incoming. This part right here, that's the incoming photon. They have a lot in this one picture. That's the incoming photon, right? It interacts with the molecule, the dot. And then look what's emitted. What happened? Did the frequency change? See? No, what I'm saying is this, I should change colors here. This guy, there's my outgoing photon. And Melissa's right. The frequency didn't change. How can you tell the frequency didn't change? Yeah, the same wavelength, right? Same wavelength. And all they're drawing is electric field. What did increase? The amplitude. That's the word you want to use, the amplitude. And notice how it's still in sync. It's still in phase, right? You could just keep extending that. It's still in phase. So it's coherent is the word. It's still in phase. And it increased the amplitude, right? So that's the makings of a what? Can you make the connection? It starts with an L. I've got a bunch of them here. A laser. That's the makings of a laser, right? So I guess we'll do smaller case. Fine, we'll do bigger case. L, A, S, E, R. Light. See if you can finish this. Light amplification. Light amplification by stimulated emission. And this is the part we haven't got yet. Resonator. And I think there'll be pictures of that at the end of the chapter. Okay. That's how they named it. Exactly. It's not just something made up. Light amplification by stimulated emission resonator. And we'll hit that again at the end of the, I think the chapter is going to be talking about that at the end. It'll have some nice pictures and all that sort of stuff. And we'll talk about what that resonator is, and we'll go over that. I just wanted to hit that. Okay. So that's the first if you're going to emit light, that's the first way. Second way. Not dark enough in here, but maybe I can turn this screen off. Can I? I thought I could. I thought I had a black button or something. Blank page? No, it's not black. I thought I had a black page. Chapter 16. Color palette. I don't. I guess I could try to make one, right? Fill black. Now I made the room a little bit darker. Okay. So, oh no, I didn't. I forgot to do what first to my little toy?
Shine light on.
Okay. So, shine some light on it. Right? Okay. So what type of emission is this? Is this stimulated emission? It's going to be the other one. What do they call the other type of emission? Spontaneous. It's just happening spontaneously. Okay? So that's the second type. Right? The molecule just spontaneously emits light. So it's hanging out in an excited state for who knows, for has to be in there for some amount of time, right? And then to reach the ground state, it just spontaneously emits light. So at some point, it's just random. So this is where we talked about it in instrumental, where there's actually two types of emission, right? And let's get some more light on this guy. Okay, so the average amount of time a molecule spends in its excited state for this to work is on the order of milliseconds. There are two types of emission that are spontaneous. What was this? Phosphorescence. Phosphorescence is this one. And then fluorescence is exact same thing, but it happens really, really fast. On the order of nanoseconds or femtoseconds or picoseconds, it's really, really fast. So that's the lifetime, the average amount of time it spends in the excited state. So this is definitely phosphorescence because it dies out after like a minute or so, right? But the average amount of time is on the order of milliseconds. I wonder if it's too dark in here for that to work. But what might be interesting is this. Oh, this died. Don't die on me. There it is. Okay, you got to be able to see this. If you can't see it, you might want to sit where you can. Okay, I wonder if it can see it. So I'm going to get this guy going really nice and bright. Now, Kevin, can you explain what this thing is that's on this computer? Could you help me build it? This thing that we're doing. What is this? Yeah. Oh, it's not sensitive enough. Okay, I'll have you play with it later. I wanted to see what the emission spectrum looked like, but it's not near sensitive enough. Okay, so we talked about those things. So we talked about two types of emission: stimulated emission, beginning of makings of a laser. Okay. Here's an idea. Now we have all these coefficients that are starting to run around with Einstein, right? Here's the coefficient of spontaneous emission is capital A. And they say that A is directly proportional to the frequency cubed. So let's see if you're following along what Einstein's really saying here. let's say you have a molecule that emits IR. You have another molecule, let's not even say IR, let's just say it emits the color blue. You have another molecule that emits the color red. Okay, those are just the colors that this molecule emits. Okay? Which molecule, we can call it molecule A and molecule B, which one would exhibit a higher rate of spontaneous emission, according to what Einstein says here? So can you make the connection?
Based on weight, is that supposed to be new?
Yeah, that's supposed to be new, raised to the third power, right? So the spontaneous emission, and this is supposed to be a directly proportional sign, so we're leaving out all the complicated, ugly stuff. The important factor for the concept is that spontaneous emission is directly proportional to the frequency cubed of the light that's being emitted. So what it comes down to really is which frequency is higher, blue or red? Which frequency is higher? Yeah, it is confusing. If you think of it this way, Roy, G, Viv, right? E equals H nu, right? There's several ways to think about this. Oh, here, I can show you with our fancy-dancy thing here. All right, here's blue. Here's blue. Okay. Here's red. Okay, now that's wavelength on the bottom. Which one has a longer wavelength? That was red. Here's green. Here's blue again. I don't know why blue has two. Blue's got two components. Whoa. Yeah, I know. Isn't that weird? Something's funky. But which one has a longer wavelength?
Yeah.
Red does, right? Red has a longer wavelength. So if red has a longer wavelength, its frequency is lower, right? You can do the math in your head, or you can just kind of think of really long wavelength. Man, look how the frequency is going to be. There's not much going past per unit time. So red's got a lower frequency. So if red has a lower frequency than blue, which one would exhibit more spontaneous emission? Blue, because it's higher frequency. And it amplifies itself 3 times. So the higher the frequency of the light, the higher the degree of spontaneous emission. That's all they're saying. So this is why, I don't even know if you realize this. When you were born, when you were growing up, they were really happy to make this. It doesn't even, why doesn't it work? Can you see it? That's my little red, my red laser. The battery's dying on it, big time. All right? So they were really happy to make these. And this is the only thing they had on the planet. It was within, I would say, maybe 10, 12 years ago. Woohoo! Why? Now we can make purple. We can make blue. We have Blu-ray players. You didn't have blue LED lasers not that long ago. Because of this. The degree of spontaneous emission is just much higher for these colors. It's much more difficult to build a laser that's at these higher frequencies.
What did you say?
Because if you want a laser, you want what type of emission? Stimulated emission. You want a small amount of What type of emission? Spontaneous. You want all stimulated. So the higher the frequency, the higher the degree of spontaneous emission. Well, which one has a higher frequency? That purple or the red? Oh, there it is. The purple, right? Higher frequency. So much more spontaneous emission. Much more difficult to build. Okay. But we have them now, so you guys don't think much of it. Let's see. Oh, I got the equation here. So Einstein showed that the stimulated emission is equal to the stimulated absorption coefficient. And A equals B times this. So that's probably going to come into some homework. Okay. Gross selection rules. Now, the one that's in here that I think you should know, if you had instrumental analysis, is this one. If a molecule is going to undergo IR absorption, it's going to, you can see this molecule on the FTIR. What has to be happening, or what's the property, what's the gross selection rule? What was it? The molecule had to have a what? Well, let's not even say that. Because what type of motion is going on for IR absorption? Vibration. So let's use the word vibration. The vibration of the molecule exhibits an O. Ooh, there we go, Padawan. Oscillating what?
Dipole.
Perfect. An oscillating dipole. What was a dipole? Alyssa, what was a dipole?
I don't remember.
What's a dipole? Somebody help her.
How do you do with the electromagnetivity of
Negativity.
negativity, yeah.
Electronegativity. So just make something polar. Just make something polar. This bond is polar. Well, if it's polar and it's vibrating, you've got an oscillating dipole. It will absorb IR. Like, that's why you see stuff like this. Carbonyl stretch. I mean, look at that. Carbon and oxygen, that's really highly polar. So those sorts of things, right? Okay. The rotational transition. Now here, I don't think you're going to... I think this is PChem lab, but no one's done it yet. And what you get is, we use the FTIR, and you have wave number down here, right? And it ends up looking like a, I don't know, angel wings or something. I can't draw it very well. Let's see, let's see if I can do a better job here.
Is this for number 1 or 2? So round.
I can't draw very well.
That's better, I think.
But these are really, really thin, and you really got to zoom up on it. You end up seeing 2 wings, almost. And this is a rotational transition. I think instrumental, you did see this. You guys saw this on the FTIR, because you used carbon monoxide or something, didn't you? And then you went out to the car, and so you zoomed up, and you should have seen a rotational spectrum.
You didn't zoom in, but yeah.
Yeah. Oh, you didn't have to zoom in. I thought you really had to zoom in. Okay, anyway, zoom in or not, you see these. I think you see a much better picture when you do the lab. But it needs to be permanent dipole moment. In other words, the molecule has to be polar. The molecule has to be polar. And if we would not have skipped chapter 15, for those of you who have had inorganic, that molecule, what's the terminology? Must be a member of one of these what groups? Point groups, right? Has to be CN, CNV, or CS. And where's this stuff coming from? There's this nice little chart, right? You start with your molecule and you do all these rotations and flips and things, and you figure out what point group it ends up in. And that just classifies its symmetry under rotation and reflection and all those sorts of things. Okay. Rotational Raman. This one has weird. This is an odd one.
I thought you said this was for number 2.
Look where I wrote it. Okay. Rotational Raman transition. Molecule exhibits. No, let's not put that word in yet. Let's just put in the word polarizability. Okay, so start with the word polarizability. Now, there's going to be an adjective in front of it, but let's just start with this first. What is polarizability? How I picture this is we have a molecule, right? They have a nucleus, but you have these clouds of what? What's it? Electrons, right? And they're in these, you can imagine what kind of ever shape they're in. But you kind of have an idea when you did some Spartan modeling, and you saw when you did you picked the models where you could see these blue areas or these red areas. Remember doing that? So you kind of think of a big kind of blob like that is that kind of shape. And it's all just electrons. The nucleus, they're not doing anything, right? It's all molecules. And so it's all electrons. They're just taking up all the space. They're really doing everything. So imagine that blob of a molecule with red regions of high electron density, blue regions of low electron density, and then you have this incoming photon. And picture it the way the author wants you to. It's just oscillating electric field coming in. And it's not even striking it. It could just be coming by it, right? Do electrons interact with electric fields? Do magnets interact with magnetic fields? Yeah, I mean, you have a magnet and you approach another magnet up close to it, and it either pushes it away or attracts it. So do electrons interact with electric fields? Yeah, because you have this plus and minus going on. It's kind of weird. Yeah, it's easy to picture a magnetic field because you just have these magnets, right? And they can do these little experiments and have these little iron filings and things. But with electric fields, I think the only thing you can pretty much do is get a Tesla coil and get close to Gloriana and zzz, or a taser, right? Even that doesn't really help you too much. But the point is they'll interact. So if that electric cloud is interacting with the incoming electric field, that's polarizing it. And the electrons are going to move. You're making it you're polarizing it. So if this cloud of electrons is perfectly spherical, no matter how you polarize it with this incoming radiation, you can rotate the molecule a little bit, nothing really happens. I mean, it's spherical. But if you rotate the little molecule and it looks different, that's called anisotropic. Anisotropic polarizability. So it's a very general, I mean, you can't get much more general than this type of gross selection rule, because pretty much what molecule is perfectly symmetric? Hardly, there's not much out there, right? So that means pretty much every molecule, it's going to exhibit anisotropic polarizability, because you can polarize it in different regions differently. So it's a very, out of all these types of spectroscopy, Raman is really one of the most widely applicable, and it can detect most anything. The Doppler, okay, so now we're talking about, now we're going on to line widths. Okay, so I brought this thing in. Hopefully it didn't shut off. Okay, he didn't. So let's see what's going on here first. Let's make sure you can recognize this stuff. I've got a couple flashlights here. What color do they look like? White, right? Okay, so if I shine this on here, on my little detector system here, what's it going to look like? All the colors? Is it going to be going up and down? Or is it just going to be a smear? Or will it be a flat line all the way across? What would it be? Flashlight. Let's try it. I guess you'd guess first. You'll remember this better. All right. I can get this going. Where is it? He's getting close. How come it's not going very high? Oh, there it is. Whoa, too much. All right, really broad. This is what radiation? Black body radiation. This is a black body emitter. It's just a little filament, right? The other flashlight, though, says what on it? LED. Is this a black body emitter? No. So you shouldn't see a... Now you should see more structure, right? And you do. In fact, the only LEDs that they have in here are the ones where it's going to make, to your eye, it looks white, but it's not true white. But only a spectrometer could tell you that. That's not true white. Okay? This is true white. That's true white. So if you go to a, I don't know, a museum or whatever, the reflection off of this light source is what they're expecting. Okay, so what I was getting at is this. We're talking about line widths of gases. Okay, so we're not talking about black body radiation or anything like that. We're talking about, take a gas, get its molecules all excited, right? They emit light, and what's the spectrum? And we're talking about atoms, too, because otherwise you're not really going to see much of a line. So if I take, I don't know what gas that is, helium or something, right? Now you looked at this, at different bulbs of this through those little spectroscopes. Remember, what did you see? Yeah. Yeah, you saw lines, right? You didn't see a smear. So that's what we should see here. If I can get it lined up right. See the lines, right? So it's just a numerical distribution of what you saw visually, all the different colored lines. Okay. But are they lines? Is there some width to them? Yeah, they all have peaks, but is there some width to it? Yeah, there's definitely some width to it. But there shouldn't be, because you have E0, E1, boom, they're gases, right? And it's not concentrated at all, so they're hardly ever colliding with each other or anything. So some funky things are going on. Why is there a width? Okay. Instrumental people. Oh, that's chromatography. What's this one? What's this thing for? Oh, turn it on. I got to the most nauseating sound. What did I do with this? There's the D, illustrating Doppler effect. So this speaker, when it's going towards you, you hear a what? higher frequency, going away from you, lower frequency. Can they stay awake now?
That sounded ugly.
Right? So that's what's going on here. In this lamp, I was holding a detector over here. Some of those atoms, right, helium atoms, they're approaching the detector. I mean, it doesn't look that big. But for a gas, come on, a tube, that's tremendous. That's miles for it. So it's traveling towards the detector when it emits. Others are traveling away from the detector when they emit. So that's the Doppler effect. Doppler broadening. That's giving rise to these line widths. Okay, that's one of the contributions. We're only going to talk about two. So that's one of the contributions. And then they have an equation for it. They even told us. All right? So if that emitter is going away from the detector.
What was
Yep.
one of the contributions?
Doppler broadening. We haven't talked about the second one yet.
The Doppler what?
Doppler broadening.
Okay.
Doppler broadening. Doppler. Or you can say Doppler effect. All right? So if the emitter is going away from the detector, right, the frequency is a little bit lower. Right? Because the denominator is bigger. Right? If you divide by a bigger number, you get a smaller answer. What's V? It's nu naught. Yeah, the frequency where nothing is moving. Right? Nothing's moving. So your source isn't moving. So that's what's coming out of the the true answer. So you divide by 1 divided by 1 plus s over c. So c is the speed of light. What's s? The speed.
Period.
It's the speed of the source, right? Because if c is the speed of light, whatever's on top has to have units of speed too. And it's going to be the speed of the source. So if the emitter is approaching the detector, right, going towards you when it emits, the denominator is now a little bit smaller, so you get a bigger number times that non-moving source frequency. Okay. So then there's some other expressions here. We haven't got there yet. The second thing. So that's contribution number 1. And we're talking the line widths of emission spectra of what again?
Yes.
Gases. Yeah, gases. Okay. Because nothing else is going to have a line, right? Solids, liquids, there's too much going on there. So Doppler broadening continued. Here's just delta nu. All that is see what they're saying? If this is frequency, and then this full width half maximum would be delta frequency. If that plot was wavelength, then that would be delta wavelength, right? It's just the width. They call it the FWHM, full width at half max. Okay, that's what these guys are. Okay. Oh, what's M? Yeah, the mass of the the source, the emitter, right? The atom, the molecule, whatever's doing the emitting, right? K, recognize K? Starts with the B. Boltzmann constant, yeah. Okay. Here's contribution number 2. right? Because we're talking about, because for us to see that light, right, it had to emit it. Well, remember we talked about, oh, phosphorescence, fluorescence. There's different, it stays in the excited state for a certain amount of time. Well, that's going to cause problems too. So we've got lifetime broadening. Okay. And we never really talked about the Heisenberg uncertainty principle, time dependent. We never really talked about it that much. And that's where this is really coming from. But the contribution to lifetime broadening, hey, what's this, is this? See if you recognize these things. Look at that. This one has no tilde. This one has a tilde. So the one with no tilde is what? That's frequency. Good. You're following this. What's the one with a tilde? Wave number. Okay, good. You're recognizing this. Okay. And if you want to use this equation, what do you think see, lifetime is tau. There's our tau. But what does the slash PS mean? This is just the author's convention. They've been doing this from day one. Yeah, no, this is where it gets confusing. I don't like how he does this, but we have to live with it. Picoseconds. If you want to use this equation, lifetime has to be in picoseconds. That's just how he does it, so we have to live with it. So if you want to use this expression, if this is in the homework, lifetime has to be in picoseconds. A picosecond is perfect, 10 to the negative 12. Okay. And then they're saying that, okay, fine, collisional deactivation. You don't want to emit light. You want to go from E1 to E0 and somehow just get there. I don't know how you get there, but you get there without emitting light. They call that the collisional deactivation. It's just dissipating your energy through heat, right? Through a lot of collisions. Okay, and that deactivation is 1 over the collision rate. When I guess that only works when each collision results in a deactivation. But okay. Natural line width, that's just the minimum. So don't do anything funky. The minimum line width that you can actually get, the narrowest. So that means pretty much just spontaneous emission is the only thing going on. And we're almost done here. Moments of inertia. So now, I wish I could show you one of these. They're changing gears now. They're talking about pure rotational spectra. I wonder if it's 2 o'clock. I wonder if I have a carbon monoxide or something. I thought I did. Let's see. I don't. I could Google it. Look, there it is. See what I was trying to draw? I was trying to draw these guys. Okay, so this is carbon dioxide. Here's a wave number, right, and an intensity. So you see this is pure rotational spectrum. And again, for you to get a pure rotational spectrum, what was the gross selection rule? The molecule had to be... No, that's for FTIR. That's for it to absorb IR. For it to have a... that was for Raman. Permanent dipole moment. So if you want to get one of these nice, pretty angel wing things going on, the molecule, we're talking about rotational transitions, you need to have a permanent dipole moment. Okay, so that's what we illustrated. So it starts with all this rotation. We're talking about rotating molecules now. And it can always be divvied up into 3 moments of inertia. 3 perpendicular moments of inertia. That's how you can describe rotational motion. 3 perpendicular moments of inertia. And what is moment of inertia? Well, it's a big I. You take each atom in the molecule, mi, its distance, right, to the center, ri, square it, add them all up. Okay. I think we talked about something like this before. We had, I think we did I is mu r squared. I'm trying to remember this. Like if we had, do you remember doing this? Does that look familiar? The moment of inertia for the moment of inertia for a diatomic molecule. The reduced mass, r was the bond length, right? And that was the moment of inertia. Right? Mu is the reduced mass. Okay, but table 16.1's got a lot of these rigid rotors. And for all this stuff to work, all these equations to work, they call them rigid rotors. This guy's spinning. But if he's spinning, it's gonna, that R should feel like it wants to get what? Bigger or smaller? If this molecule's spinning, the way it's drawn. Can you imagine it? Yeah, don't you feel like R is going to get bigger? Call it centrifugal distortion. I don't think that's on here. We're not worried about that, I guess. But this cannot bend. It can't stretch. It can't stretch. That's why they call them rigid rotors. So if this does get bigger, then all these equations go to pot. This isn't going to work. So all this stuff is rigid rotors. And they've got table 16.1 on page 464 lists a lot of this stuff. Okay. So it doesn't distort, right? There's no distortion when you rotate. Those bond lengths aren't changing. So if you have a, on that page 464, they talked about all these different rigid rotors, and you have spherical rigid rotors where things are perfectly spherical symmetry kind of, and they have 3 identical moments of inertia. I don't know if this stuff even fits in with the homework. Probably not. Probably don't think you need to really worry about this stuff. Symmetric rotor. Remember, there's 3 moments of inertia to characterize any molecule. So spherical, all 3 are the same. Symmetric, 2 are the same. 2 of those moments of inertia, right? And I don't know where this stuff is coming from. I think I'm big on this symmetry stuff because we just typically come off of chapter 15. So it has a 3-fold symmetry. That won't even mean anything to you if you haven't had inorganic.
What
right?
say 2 same what?
2 of the same moments of inertia. And I think we should probably take a look at page 464, but we're running out of time. It doesn't really, I don't think it really matters though. If you have 1 moment of inertia equal to 0, right? Linear rotor, all diatomics are linear rotors. Right? Kind of like linear rotor. Asymmetric, 2-fold symmetry or less. Again, I don't know if that's going to help you much, but maybe that's 3 different moments of inertia. So this is, all I'm doing is pretty much writing down the main ideas from this page 464 table 16.1. And I should probably copy paste that. But that's kind of where it's all coming from. And now there's little equations for all the moments of inertia for these different types of rotors. They're all rigid. They all can't change under rotation. They all won't distort. And on page 460, they talk about the Boltzmann distribution. I guess we need that for question 20. Okay, the numbers of atoms or molecules in different states, their population. That's what Boltzmann distribution is all about. So we're pretty much out of time.